Hello everyone. So this is another math video, the second one. If not, if I recall correctly. So yeah, today I'm going to talk about the solution walkthrough to IMO Shortlist 2009 combinatorics problem 8, which was also the last problem on the shortlist. There were a few reasons that I'm doing this video. So first of all, it was proposed by Gerhard Woeginger, who unfortunately passed away in early April, and I only found out after like a few months. So I guess this was in a way like honoring this problem proposal as well, since after all he also proposed quite a number of IMO problems themselves, and his problem proposals were simply excellent. The second reason is that combinatorics was not something that I was strong at during my math Olympiad time. I was stronger in geometry and number theory, in fact. And this combinatorics problem is one of the very few, like honestly, one of the very few combinatorics problems that I could solve uh, uh, well within a contest time, although like only very recently. So yeah, I think that maybe I have like a good chemistry with this problem, and therefore I think it's worth to talk about this. And the last reason is that I already have this material with me, this like slides with me because I talk about this for the Malaysian IMO team in early July before they flew off to Norway for the actual competition. And by the way, they did pretty well, I should say, with one gold medal. So yeah, it makes my life easy to make a presentation like this on YouTube. Okay, so let's talk about the problem statement. So this problem is about a number, and a function. So let's say our number is n over here, and let's say r is the last digit, the rightmost digit. Our function h will do the following. If the last digit is 0, then it's easy. You just remove the 0. If the last digit is not 0, then you gotta make the string, the number bigger by doing the following. First of all, you split the numbers into L and R. We will call this as LR decomposition later. The left part and the right part LR is such that the right part is all the digits that are at least R, and such that this R is also, the capital R is also maximum, and the left digit is just whatever in the remaining. So if you look at the example down here, we have like what 17151345543. In this case, the last digit is 3, so R is just any the longest possible string such that all the digits are at least 3, and then left is something that ends with 1. So in this case it ends with 1, but in general it's just like anything that ends less than 3, or if this is empty, it could be empty as well. Okay, so now enough with the decomposition. So what you would do right now is that you keep the L, but you consider R minus 1, which means that you change this 3 to 2, and then you copy it. So you have like 2 copies of this R minus 1 over here. So this is how you create h of n. Now the problem asks you to show that starting with any arbitrary integer greater or equal to 2, if you apply this finitely many times, then you will get the number 1 in the end. So I think one difficulty of this question is that this result is pretty much unbelievable because just think about it, like your number string is just going to be longer and longer after this. So how do you expect to be compressed to one in the end? Yeah, and indeed, if you think about the number of steps required just consider those numbers that are pretty small. If you start with n equals to 2, sure, you end up with 7 steps. If you start with n equals to 3, then yeah, it's still not very big. It's 206 steps. If you start with n equals to 4, though, it takes like 2.8 times 10 to the 38 steps. And anything more than 5, yeah, I'll leave you guys as an exercise. And by the way, these are from this user called Lucky Toilet out of problem solving. So from here, you can see that like even starting with like a very small number, you need like a lot of steps before it goes to one. And therefore, it kind of shows that this process is the journey to one is not that trivial, and therefore is part of the difficulty of this problem. So what are the key techniques that I'm going to talk about today? Which is these are basically the way that I solve the problem. So first of all, it's called problem reduction because you have like left part and right part, and every time you do this, if you do this enough times, right, you probably notice that the left and the right part for every time is not the same because it really depends on what your last digit is. So it would be really nice if you can just split it into left and right in the very beginning and just say that, okay, for this very example, we only care that the left is going to just be the same, and the right, we will just work on the right part and just wait for the right part to vanish, and then we worry about the left part later. So that is, in fact, one of the special cases that I will talk about later. The second one is to try small cases. Well, from you can from what I show you just now, like the numbers 2, 3, 4, you probably would notice that yeah, these are not the small cases that you want to work with. So so I guess the context is that when solving combinatorics problems, one of the tricks people would tell you is that yeah, just try some small cases and see what are the patterns and see how you can generalize. But here it's tricky to find such a small case, and I will talk about what the actual small case is. And the final thing is you want to do induction. Induction is useful, but also on the right quantity. So there are many things that you can induct on, and a lot of the induction approach would fail. So yeah, that's another thing that it makes this problem interesting. Another thing is to program your mind in the following sense. So here we will treat each number as a string instead of the numbers itself and the digits as characters. So what this means is that when I talk about like when the number is 2022, then you literally treat this as a string 2, 0, 2, and 2 instead of like just treating it as one number. And another thing is that our goal, instead of reaching empty string, instead of reaching the number one, we want to go even further and go and reach empty string instead. So one question you might naturally ask is that how does empty string imply that we have already solved the problem? Well, the truth is that if we can go from any number to an empty string in the end, then it must pass by one somewhere in the middle. And I guess I guess it's fair to say that this is left as an exercise for the reader, and because it is not that it's not that hard to prove after all. Okay, so now let's talk about problem reduction. So in this case, the reduction that we are talking about is what if you have 0 in the middle? So the lemma here is that if let's say x is empty set reducible, meaning that it goes to empty set after k is such iterations of h for some finite k, and same goes to y, then so is the string x0y, meaning that you just concatenate everything, starting from all the digits of x in that order, and then insert 0, and then insert y in that order. And how do you show this? Well, this is not that hard to show. As per the problem statement, R cannot contain character 0. Why? Because so recall that if the last digit is 0, then you just get rid of the 0. If the last digit is not 0, then R, the right part, will basically has the digits that are at least small r, which is greater or equal to 0. So R does not have any character 0. So this means that 0 has to be part of the left string. And that means that you basically, and anything that you copy like like R cannot have 0, and the only time you would copy a 0 is when the last digit is 1, and then you R minus 1 is 0, and then you just copy the 0. But the essence here is that h of x0 y, you can just think of it as h x0 of and then h of y. And if you so this is just one step of the iterations. What if you do two steps from x0 hy, then because there is a zero here, then you end up with like x0 hy and then x0 hy. This will happen all the way until you get until y vanishes. So because we already assumed that y will vanish after some time of applying this one, so so the whole iteration goes with like x0 y and then x0 hy blah 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 until this y is gone, and then you are left with x0, and then because it's zero, then zero is then you just cut the zero out, and then you are left with x, and then x by our induction hypothesis is it also goes to empty string in the end, so you do live with an empty string. All right, so this is the problem reduction that we are interested in. You'll see why this problem reduction is important later. Now let's talk about small cases. Here it is, yeah. I'll just reiterate that the many like a lot of the times where for combinatorics you want the small cases are indeed the conventional small cases that we might think about. So you try with like small numbers here, yeah, n equals to 2, yeah. There are only seven steps, but you probably wouldn't see how this generalizes to the general setting. When n equals to 3, well, there are only 200 plus. Okay, only is a bad term. There are 200 plus steps, but you can probably finish it in like maybe 10 minutes, I guess. Sure, just push through and see what are the things that we can get out of. Now n equals to 4, 10 to the 38 steps. What the heck, man? So all these things just tells us that we need different small cases. And here one hint you can get from here is that the complexity maybe doesn't come from the length of the string itself, but from the magnitude of the digits. So meaning that like when like 2 is like way more complicated than the digit 1, and then 3 is way more complicated than the digit 2, and 4, yeah, I don't even have to say. So if you want to start something that is really simple, then how about just stick your strings to 0 and 1, and that's indeed our small case that would work. So yeah, let's try binary strings 0 and 1, where you have this one. Now here you can see why the reduction lemma would be useful, because binary string in essence is just like blocks of like consecutive zeros, consecutive ones, consecutive zeros, consecutive ones, etc. So so when you have consecutive zeros, you can basically cut into two parts and just worry about the right part first. So so in other words, we can just consider each consecutive blocks of ones individually. Now, if you want to make the problem simpler, then you can say that, okay, if there's only one, then you probably know how to make it go to empty string. If there's 11, or in our case, we should see it as 1, not 11, because we want to view things as strings. Then yeah, there aren't that many steps to do either. It goes to empty set in the end. But what if you have 1, Now the next step you see it is gonna be 1, 1, 0, 1, 1, 0. However, by our reduction lemma, there's a 0 here. By our reduction lemma, we can do this 1, 1. This is the last 0 is gonna is the first to vanish, and we can just worry about about this 1, 1, and by our reduction by our induction hypothesis over here, this would go to empty string. So the next one, this will go to empty string as well, and finally the leftmost 1, 1 also goes to empty string. So it follows that 1, 1, 1, the 3 ones do go to empty string. And in general, if you have n ones, it will become n minus 1 once over here, and then 0, and then n minus 1 once over here. Well, there should be a 0 here after this, no, after this string, but well, 0 is going is going to go away in the first step itself, so it doesn't matter. So by now, I hope you can already see that if you have n ones, then it will go to empty string eventually. So yes, we have solved for the case of binary string. Now, the next thing is to induct properly. So in general, in general, you might be able to see that, like, okay, from binary string, you want to extend this statement to maybe strings that contain only 0, 1, 2, and then from 0, 1, 2, you want to go to 0, 1, 2, 3, and blah 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 blah. In general, let's say that all strings with characters from 0 to D are like empty string reducible, meaning that it will go to empty string in the end. Now you want to make this true even when D plus 1 is introduced. So okay, this K is supposed to be D actually. Sorry for the typo. So for the next set of the conversation, we'll just treat D equals to 8, meaning that let's just cheat and say that, okay, assume that we have already done the job for 0, 1, 2, blah 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 until 8, and now extend it to 0, 1, 2 all the way to 9, which is exactly this set of numbers that we really want. Now, one thing that we can induct is the number of occurrences of D plus 1, the new digit. But this is probably not gonna work because recall that this new digit is very likely to be copied anyway. So for example, if you start with 9, 8, it becomes later on it becomes 9, 7, 9, 7. So from 1 9s it becomes 2 9s, and then God knows how many 9s it's gonna produce in the end. Now, what if we are allowed to delete the last digit when it's 1? So yeah, this is actually part of my thought process, because because when I was thinking about this puzzle, then of course the first thing that I thought about is the number of occurrences of this 9, but it as you can probably tell, it doesn't work. Then I would say, okay, what if we are allowed to delete 1? So to spoil the suspense, you are if you are allowed to delete the last digit when it's 1, you are basically treat the whole puzzle as if we are doing all the digits from exclusively between like 1, 2, 3 all the way to D plus 1. And since we are allowed to delete 1, this is no different than the original problem where you are only allowed to delete 0, but with only characters from 0 to D. And by our induction hypothesis, all the strings with characters in 0 to D are empty-string reducible. So it does follow that in this case, right? Like our new set is also like empty-string reducible. But of course, this is not how you should write the solution of the problem. It just gives you a new motivation on how you should proceed. So yeah, what do we induct on? So I should before I proceed, I should say that here we have 2 layers of induction. The outer layer is the set of the characters you consider from 0 to 8 to 0 to 9. The second layer, or the inner layer of the induction, is some sort of complexity of the string. Well, you'll see what do I mean by the complexity later. Now, before that, let's do some let's do some warm up. So here let's just consider like n with non-zero digits, because again, by reduction lemma, if there's a 0 in between, then we just have to worry about the left part and the right part, and therefore anything that has like non-zero that has 0, just it just like doesn't really matter, right? That means that we can define this thing called the predecessor function. So let's say if n only has non-zero digits, then you can consider like its predecessor as in like all the digits that is minus reduced by one, and of course the successor function of the smaller class. So let's say let's say you have, if there's a string of digits that is only from 0 to 8, then you can define the successor function as as if you just add all the digits by one, and then all the digits will be between 1 and 9. So I've given an example over here. So 2 4 5 3, you add 1 to all the digits, becomes 3 5 6 4, and then for predecessor you just you just reverse it. Now let's consider the LR decomposition. So here's the fun part. The no, so one thing is that between the predecessor and the successor function, it just turned out that the way you cut it turned out to be the same. So what do I mean? So here you have, like, for example, I have like 3 5 7 6 and 4 6 8 7. It just happened that for both of them, the LR you cut it, it's determined by cutting in the middle. And then when you copy the R part minus one, it also follows the same pattern as in that you see it here, 3 5 7 5 7 5. If you add one to all the digits, it will become 4 6 8 6 8 6. So the one good thing about this thing is that this is true in general, provided that the last digit of the predecessor over here is not equal to zero. And you can show quite easily that whenever this n prime, the last digit, is not zero, the LR decomposition of n also follows the same pattern. Now, what happens if the last digit is zero? So here, from 370, it just becomes 37. But if you add one to everything, 481, then unfortunately the string just becomes longer, 480 480. Now, here there's a beautiful property as well from this apparent complexity. So from zero you become one, and one is the smallest non-zero digit. So it does follow that, and because like our successor does not have any any zero, so all the whole string does get copied into the R part. So meaning that L here is just an empty string, and then it becomes 480 after this hash function. And see, we have 0 over here. This we can just operate on each 48 independently. So from 37, and then 48 is the successor of 37. And just to remind yourself again, notice that how I use 3748 versus instead of 37 and 48, because we really don't want to treat them as a number. We don't want to treat them as a number, but we want to treat them as strings. So here in general, h of n, which is also to the h of the successor of n prime, has the following form. If the last digit of n prime is greater than 0, then you just have s of h of n prime. Whereas if the last digit is 0, then you also have s of h of n prime, but with a 0 here, and s of h of n prime with a 0 in the end. So by now, let me just get this. So by now, I hope that you can see kind of a bit of how we should proceed with this induction. So here, we call that for the outer layer, we induct on the set of characters or digits that we allow, aka like 0 1 or 0 1 2, or 0 1 2 all the way to 8, or 0 1 2 all the way to 9. Here, the inner layer of the induction is that what is the number of steps we need for our predecessor string to go to empty string. So here, let's say that f of n prime. So let's say n prime is our smallest set from that contains only digits from 0 to 8. Suppose that f of n prime is the number of steps that it takes for n prime, which is the predecessor of n, to reach empty string. So by our outer induction hypothesis, this is less than infinity. So base case where if like, okay, so this is a typo. If this is supposed to be empty string, this is supposed to be 0 because like at n prime here, n prime is empty string. So it does follow that if you add all the digits by 1 to an empty string, it will still be empty string. So there's nothing to prove. Now for the induction hypothesis, suppose that um, for some k greater or equal to 1, for all the n prime where f of n prime is less than or equal to 1, k minus 1, meaning that the predecessor takes strictly less than k steps to go to infinity, the successor itself will also take only finite steps to go to empty string. So now we want to extend this statement to what happens when n prime f of n prime equals to k, meaning that it will take this predecessor will take k steps to go to go to empty string. So recall from before that this h of n is either s of h of the successor of h of n prime, or the successor of h of n prime 0, the successor of h of n prime 0. Now, here I hope that you can see how we should finish it, because even with this this longer string over here, by our reduction lemma, we only need to consider this like h, the successor of h of n prime, to go to an empty string, meaning that we can deal with this two s of h of n prime independently. And by our induction hypothesis, since okay, so here f so here, right, we have like h of n prime is equals to is equal to k minus 1. So it does follow that the f of s of h of n prime, okay, this is getting a bit complicated. So this is less than infinity. So I think this part I probably need to rephrase. So yeah, here we have this we have this number n, and then here we also have that h of n is like the successor of either the successor of h of n prime, or this string copied two times with zero in between. But we know that n prime takes k steps to go to empty string, and h of n prime, because we already apply one h, it will take k minus 1 steps. And by our induction hypothesis, if h of n prime takes only k minus 1 steps, then its successor will take finitely many steps to go to empty string. So meaning that this s of h of n prime do go away after some time. So this one will go away, it becomes empty string. This one, and then this is gone, and finally the left part, the s of h of n prime, will also be gone. So this is how you organize the solution. So to show that I actually have a solution, I do post it on the art of problem solving. I guess you guys can have a look when you have time. And finally, since I talk about big numbers, I should talk about some asides. So I should probably say that this slide doesn't have any content. But my point is that if you think that the number of steps for the numbers to go to empty string is really big, like for example 4, you have like 10 to the 38. Well, let me just say that there are even like bigger numbers out there. Like for example, like the following year in IMO 2010, problem 5 that deals with coins and boxes. The number of coins that can potentially land in the last box can be really, yes, can be really big, and this is what tricked a lot of the contestants from what I heard. If you think that this is bad enough, well, there's this busy viewer function where, okay, I'm not going to go into the details, but the short summary here is that we don't even have an efficient way to quantify how big this number is. And of course, this maximum shift functions is the square of this busy viewer function. So it's probably even bigger. Yeah, I mean, yeah, I guess from here we can we can tell like how the proposal like came up with all these ideas. I mean, okay, if you do a bit of research on his profile, you'll notice that he works on like theoretical computer science, and he was like really interested in all those like P equals NP problems. So I wouldn't, yeah, I think I wouldn't be surprised that he will, yeah, he would also be interested in like all those like, yeah, like big numbers like Turing machine stuff. So yeah, this is all the presentation I have. Yeah, thanks for listening. I'll hopefully see you in the next video.